Okay, week 2 of Lab 8, last lab of the semester. Last time we talked about the theory behind the infrared spectrum of HCl, and we talked about the rotational levels and vibrational levels and the couplings and the corrections for anharmonicity and for bond stretching, and how you interpret the spectrum in order to get molecular parameters out. We'll talk a little bit more about that down below, but before we do that, there's this topic we skipped last time, which is how the FTIR spectrometer works. I'm no expert in this at all, so this will be very low level, but here's the gist of it. So if you have a conventional, what's called a dispersive spectrometer, the way that works is that you have some source of light, and it covers, polychromatic means it covers a broad spectrum of colors or wavelengths. And then there's a dispersive element, either either a grating or a prism. In more modern ones, it tends to be a grating, but there are times when prisms are appropriate. And what that does is spread the wavelengths out, right? It's just like a prism. You get white light in, white sunlight in, and red, blue, green, and so on out. And the same is true, of course, in the IR spectrum. You get a range of IR frequencies spread out in angle, and then you just put a slit in front of those so that the light that's actually hitting your sample is one particular relatively pure wavelength. And then you just measure the absorption, and then you rotate the mirror usually, or the grating usually, and in that way you get a whole range of wavelengths impinging on the sample, and that's how you get your spectrum. There are a couple of troubles with that. The first is that the amount of light you put in is getting cut down by some enormous factor by the slit, right? Almost all the light that you put in isn't getting through the slit. And you can fix that by widening the slits, but now you're letting in more wavelengths as well, and that hurts your spectral resolution. So there's always this trade-off between spectral resolution and the ability to get a signal at all, right? If your light is too low, you just can't get a signal, and in a reasonable length of time anyway, and so there's always that trade-off. On the other hand, an FTIR spectrometer works in a very different way. There's a source, probably the same kind of source as in the last case, a light with a whole lot of broadband light, polychromatic light comes in, so a lot of wavelengths present, basically white light in the IR region of the spectrum. And it goes through a polarizer so that it's all polarized in the same direction so that interference is possible, because this is an interferometer here in the middle. You got to have interference, right? Light polarized this way and light polarized that way won't interfere with each other. So I'm not sure. I don't actually know this stuff very well, but I'm pretty sure there has to be a polarizer in here. Anyway, the light comes in and it hits a beam splitter. Sometimes that's a prism, sometimes it's a partially silvered mirror, but it means half the light goes this way, half the light goes that way. They bounce off of these mirrors and come back, and then they recombine in this interference region. And the result of that is that depending on which wavelengths are present, you get a wavelength modulated intensity coming out. All of that hits the sample, so it's not monochromatic light that's hitting the sample anymore. It's still all wavelengths present, but wavelength number 1 has higher intensity than wavelength number 2, and so on. And so you're modulating the intensity according to wavelength. That's what the interferometer does for you. And then that reaches the detector and you collect a signal over time. But that signal now isn't as simple to interpret as in this case, right? Up in here, the intensity you got as you sweep the wavelengths gives you your spectrum directly. In this case, since you're sending in this broadband light every time, you're getting a funny thing. You're not going to get a spectrum directly. You got to do some offline processing in order to get the spectrum, and we'll talk about that. All right, here's what happens in the interferometer region. You've got one pure wavelength, let's say. I mean, there's many present, but let's spread out or pick out one particular pure wavelength. It travels a certain distance L here and then comes back, and that means it's got a certain phase. This function gives the phase of the light when it arrives at the mirror or at the beam splitter here. And this one has traveled a different distance because this mirror is movable, and the delta L here is the difference in distances between this mirror and this mirror. So this guy arrives with a different phase. And because they're out of phase, they can interfere with each other. That's what gives rise to the intensity modulation I talked about above. And here's the math of that. Here's one wave. Here's the other wave with its different phase. The intensity is proportional to the square, the complex square of that. So these are complex waves, which is convenient mathematically, which is, yeah, E star times E, so complex conjugate of E times E. And you do out the algebra, and you get that the intensity depends on, this K is called the wave vector. And it's equal to 2 pi over lambda. So it's reflecting changes in the wavelength. So as you put in a whole bunch of wavelengths, what comes out is still a whole bunch of wavelengths, parameterized here with this wave vector quantity or wave number quantity called K, but now modulated in intensity. So they're not all equal intensity. Some wavelengths have higher intensity than others, and so on. And that's what goes into the sample, and that means that the thing you actually measure, the thing your detector actually sees here and records for you, is a superposition of intensity factors that come from the sample, among other things, times this modulation that's due to the interferometer of cosine KL. So the intensity that you get out, the signal that you measure, is a Fourier transform of the signal of the spectrum that you want. This S0 is what you actually want. This integral modulated by the cosine is what you actually get. You've got to deconvolute or invert that integral in effect. And the way you do that is with an inverse Fourier transform, which I won't talk about very much, but Fourier transforms are ubiquitous. If you're unfamiliar with Fourier transforms now, and I think many of you are, then I urge you strongly to do what you can to learn about them, because if you stay in any branch of quantitative science or engineering, especially engineering, actually, you'll encounter Fourier transforms right and left. They should really be taught in detail at the undergraduate level. I'm not sure. I guess it's just for lack of time that we don't get to them. And after all, we're a chemistry department, and a Fourier transform is basically a pure math subject. But still, it's so widespread and so useful and so ubiquitous that somewhere in the chemistry curriculum we ought to talk about them. All right, so that means here's the Fourier transform. Here's the inverse Fourier transform. You've got to do this integral. Over the decades, computers and software and mathematical analysis methods have become extremely efficient at doing these kinds of integrals, doing these kinds of transforms, because they're so ubiquitous and widespread and useful. There's something called the FFT, fast Fourier transform, that's now embedded in the software of an uncountable number of instruments and other pieces of software. Actually, the STM, the images the Fourier transformed images that gave the spots for the lattice of the graphite uses an FFT. I have no doubt. I haven't checked that out directly, but it's so ubiquitous that it's got to be an FFT. All right, and what that gives you is the actual transform, and that's how an FTIR spectrum works. A couple more details. First of all, the source is often a piece of silicon carbide heated to a high temperature to give you a black body radiation output. So this is what actually goes into the interferometer. It's got a broad range of wavelengths because it's just a hot body, and you'd get almost the same spectrum for almost any material heated to the same temperature. Yeah. Second thing is, yes, that we didn't actually take a spectrum this year. I just supplied the spectra to you, but when we did take the spectra, in fact, the spectra that I sent to you were created with 64 scans. In other words, this mirror up here, this moving mirror, this one, went back and forth 64 times, and the signal was integrated and averaged in the computer from the detector. In other words, we're building up slowly to get the Fourier transform that we need, and then we Fourier transform that to get the spectrum. And third, yeah, there are many things that I've left out on the spectrometer. Partly that's my own ignorance, partly that's because we don't, this isn't an instrumental class per se, so we don't want to spend too much time on it. But FTIR spectrometers are very common and very widely used in very many fields, so it's very likely you'll encounter them again, and it's therefore probably wise to learn what you can more about how they work. We went through these things last time, switching now to the analysis of our data. We went through these things last time, and I won't go through them again here because they're in the notes. You can read them for yourself, and they're also in last time's lecture. Instead, let's skip down and talk about what we're actually going to do with the data. I said last time that the thing you do is plot the peak positions versus this n value, which is essentially a sort of a transformed quantum number. And that gives you a third order expression for the peak position as a function of this n quantum number. And each of the coefficients in that third order polynomial is related to these molecular parameters. And so when you get out your fit, which you can get from Excel and a variety of other things, there will be a zero order coefficient, a first order one, a second order one, a third order one, and each of those will be equal to these various parameters that come from the theory. And so the third order coefficient gives you this quantity d, which is the bond stretching correction constant, right, from the rotations. The second order coefficient, gives you alpha sub e, which is the coupling constant between the rotations and vibrations. The first order coefficient gives you this quantity, but now that you've got alpha sub e, you can solve it for b sub e, which is the fundamental rotational spacing constant. This is beta here, and so you've got beta, you've got alpha e from the second order coefficient, and you can get b sub e. And then finally, the zero order coefficient is related to these two quantities. That's the fundamental vibration frequency for the vibrations, and this is the anharmonic correction for the vibrations. And since you have, and this is alpha, since you have alpha, and since, I didn't say it, but from over here in the third order correction term, you can get the fundamental vibration frequency, that means you can get this correction, anharmonic correction factor as well. Okay, so you can get this guy, this guy, this guy, and this guy. What can you do with them? They're rather abstract parameters as they are, but for the Morse potential, this quantity d is related to b sub e, which you get from this guy, and nu sub e, which you want, right? That's the fundamental vibration frequency. You're going to need it over here, but you will also, it's also a quantity of fundamental interest in its own right, because that fundamental vibration frequency is related to the force constant for the bond that's holding the hydrogen and chlorine together. And so if you've got this guy, you can extract the force constant. Also, well, I'll come back to that. From this guy, you can get from this guy here is related to the moment of inertia for the HCl molecule, which in the rigid rotor approximation at least is proportional to mu times the bond length squared. And so from this guy, you can get the bond length of the HCl molecule, and you can compare all these values, like the force constant, the bond length, even these rawer parameters you can compare to literature values. And then finally, from this coupling down here, that's related, for the Morse potential again, that's related to the fundamental frequency, but also related to the well depth for the Morse potential, so you can get that quantity. Once you've got the well depth and the force constant here, you can come back, and the relationship between the force constant, the well depth, and this sharpness parameter for the Morse potential again is this one. So you can get this A value, which is the quantity that appears here in the Morse potential. And that means that you've got this, you've got this, you've got this, right? All from your spectrum. You can plot the Morse potential itself and know, at least an approximation, of what the interatomic potential, the full interatomic potential is between the H and Cl atoms in the HCl molecule. So it's quite a complete characterization. You can get the bond length, you can get the spacings between the rotational levels, and you can get an approximation at least to the full interatomic potential between the HCl atoms. For the discussion in your write-up, here's some suggestions. You can talk about the meaning of the various parameters. I've just been talking a little bit about that up above, but there's more to say about that, and I invite you to use your creativity and imagination to say cool things. You can compare what you get for hydrogen with what you get for deuterium. The only difference between those two really is that the reduced mass is different for the two. And the question is, do the differences you see all agree with just a difference in the reduced mass, or is there some other effects that are coming in? There actually, I think, are small effects due to the fact that the chemistry is slightly different for beyond just the reduced mass. The chemistry is still a little bit slightly different for DCl than for HCl. And then finally, yes, there are these. There's the ability to predict the intensities of the peaks in the spectrum. We talked about that last time. I didn't talk about it this time, but good enough. And you can compare that to what you predict from the expressions that we talked about last time. All right. That is it for this time. Good luck, everybody, on this very last lab write-up.